Hello, good afternoon, everybody. I am Moh Haghighat. I am a senior principal engineer from Intel, and I work on advanced development in the web technologies. I also lead Intel's HTML5 technical strategy. I have had the privilege of working with Mozilla guys on web technology since 2007, and we have been doing a lot of exciting work together. Today I will be talking about the next leap in JavaScript performance. Basically, I'll be telling you what I think is the next major direction where improvement in JavaScript performance will be focused. I think that would be in exposing the compute power of the modern platforms. Modern platforms have tremendous compute power, in particular in terms of hardware parallelism at all levels. And we need to bring that power to the web platform. I'll start with a quick overview of our vision on HTML5, and then I'll talk about some exciting work that is going on in exposing these compute capabilities of the modern hardware to the web platform. Then I will talk about how you can use this compute power, in particular, how we can bring perceptual computing to the web platform so you can interact with your devices in an intuitive and natural way. And at the end, I will also talk about JavaScript penetration in some new areas, such as IoT area. So we think really big of HTML5. We think it is a game changer. If we look at the PC era, like looking at it in the past 2 decades, we see we started with native apps. Applications were distributed using CDs as binaries. And then came along the web browser. It changed the way computers are programmed forever. The change, the impact was really profound. Now think if we didn't have the web. Now, what would we have instead of the billions of pages that are out there? If we didn't have the very powerful concept of URL that weaves together all these applications, what would we have? What would we have in place of the really powerful search engines that our life today is dependent on? You get the answer even before you type that. It is all thanks to the open web platform. We believe the same cycle is happening again in mobile. Today, mobile apps are all from all these walled garden platforms. They run only on the platform they were designed for. HTML5, we think it's a web reaction to these walled gardens. A lot of capabilities are being added to the web platform to close the gap. And it is basically taking us closer and closer to the notion of writing once, running on any device, anywhere. Similar to browser that delivered the notion of writing once and running on any browser, on any operating system, on any platform. So these are quotes from the top 3 forces in software industry: Apple, Google, and Microsoft. And basically, all of them are saying that the future is in the web platform. In particular, the quote from Eric Schmidt says that as he look at it, HTML5 will be the way ultimately all applications are developed, including those on smartphones. This is quite striking from the chairman of the company that owns the Android platform. He too sees the future is in the web platform. The web model is fundamentally superior. Now, IoT is making it even more compelling. All these gadgets are connected to web, around the web. Web is the hub of all devices that compute and connect. And these devices create content that can be used, as well as they can consume content from the web. Now, a major enabler of the web platform, and HTML5 in particular, is the tremendous performance improvement of JavaScript. Over the past 7 years, 6-7 years, JavaScript performance has improved by over 100 times, a couple 100 times faster. And that is mainly to the arrival, thanks to the arrival of JavaScript just-in-time compiler. And it's getting better and better. Here are some results from SIMDJS project at Mozilla. And you basically see that the performance of optimized JavaScript on SIMDJS is within the range of 1.5x slower than the highly optimized C++ code. This is really big deal. So you have the flexibility of JavaScript, but almost the performance of native code. And a lot of work has gone to make this happen. So you may say, and then again, this data is from a couple months back from our friends in Mozilla, and most probably they have even improved it further. You may say that, okay, so performance is great. The catch here is that the base here is single-threaded, scalar native code. Now, modern hardware architects have turned to parallelism for delivering performance within a constrained budget. If you really want to improve performance by frequency scaling, then the power is roughly a cubic function. That is, if you double your frequency, your power can go up by a factor of 8. That you will hit the power wall quickly, in addition to the complexity of making more complicated single processor design. So the architecture of all modern processors have shifted to parallelism. And this parallelism is at all levels. At the core level, it means you have multiple cores. In a vector level, that means instruction can execute operate on multiple data at the same time. If you do not take advantage of these capabilities, essentially your performance is flat. I mean, the improvements in microarchitecture is very incremental. So if you want to be on the Moore's law is alive and going forward, but there has been a shift to parallelism. Now, if we look at the web platform, the browser architecture, these are the components of that. And you basically see, we have the front end, which we parse and build the DOM, and then the layout engine that decides where things go, and the rendering engine, which renders that. And then with JavaScript, you manipulate the DOM properties by interaction as well as by programming. But if you look at the cycles spent on this component, you see that only the rendering part is really taking full advantage of modern processor, the GPUs, and that is highly parallel. But the rest are essentially not scalable. And this doesn't really make sense, because if you remember, the Web 2.0 vision was the browser is your operating system. You can't say, I have an operating system which is not scalable. So this has to be solved. And there has started improvement coming along. Now I'll talk about some of them, and we'll focus on one particular area. So one area is essentially background just-in-time compilation. We, back in the context of the very first JavaScript just-in-time compiler in Firefox, we prototyped this background jitting. That is, instead of the interpreter waiting for the compiler to compile and continue execution, it continues the execution while the JIT is working on compiling. Now, these things happen in parallel. Now, if you have multi-core, you are fully taking advantage, well, you're taking advantage of that parallelism. And that, when we did that, this was right before any JavaScript JIT was developed. But then, back in 2010, IE adopted that. Today, very glad all browsers have background just-in-time compilation, parallel compilation. Now, the code that you see here is, the chart is essentially from Citadel demo from Mozilla, and then you see at the beginning, all threads are compiling code. And if you have watched Steve Souther's HTTP archive data, you see the code size, it keeps increasing, and that means they can benefit more from this compute power. That is one area. Now, another area is the layout engine. Again, we prototyped and showed that the CSS engine can significantly improve by taking advantage of multicore. And again, published. And we at Intel have also sponsored research at Berkeley, at UC Irvine, in this area. And kudos to Mozilla for starting the Servo project, which is basically an attempt to redesign the browser for the modern hardware, including multi-core, vectors, a GPU, in addition to security and scalar performance. Another work from Intel was the work from Intel Labs, the concept of parallel arrays, where in addition to regular map, you basically can operate on an array in a parallel fashion. This initially was Intel project, but together with Mozilla, now there has been more progress. And the attempt here is to make the parallelism, the hardware parallelism, available to the web platform and make it programmable. Now, the area that I will focus today and show you demos is SIMD. SIMD stands for Single Instruction Multiple Data. As opposed to, say, if you had 4 pairs of numbers that you wanted to add, with scalar operation, you had to do 4 addition, load them, add them, store them. If you use vector instructions, like you have vectors of length 4, you can do 1 addition, but with 1 addition, 1 vector addition, you essentially accomplish 4 additions. Now, in the latest version of like Intel processor, we have even wider vector instruction. This is vector of length 4, we have vector of 8, and even 16. So essentially, you are talking about speedups of 4x, 8x, and so on. We have instructions on the latest Intel processor, the shuffle instruction that operates on a 16-word data. Essentially, you can transpose a 4x4 matrix using just 1 single instruction. We want to bring that compute power to the web platform. So when SIMD capabilities were introduced, we worked on constructs, programming that you could actually use that. Say you want to find average of an array. Well, sequentially, you just get your sum, and then you add every element. So you go through the whole array, and at the end, you have the sum total. You divide it by the number, you get the average. But with vectors, you declare a variable of vector, like here, float times 4. Now, in each iteration, when you say sum plus equal list j, 4 data keeps added to the partial sum. And at the end, you sum them together and you find the average. Essentially, what happens here is you shrink the trip count of the loop by a factor of 4, and you can get a 4x speed up and more. So now, and you see on the right side, these C++ compilers can generate really efficient code. That highlighted instruction essentially accomplishes 4 addition. Now, in JavaScript, this is not possible. So we start, who better than Brandon Ike, creator of JavaScript, to talk to? We talked to our friends at Mozilla and said, we want to help bring this to the web platform. And so my colleague Peter Jensen is in the audience. He prototyped a solution using typed arrays. And then we showed speed up. And then around the same time, colleague John McCutcheon from Google is working on the same thing for the language Dart that Google is developing. So Brandon invited him to the collaboration, and we look at the API that he had. We thought it was pretty good. It needed some enhancement to work for JavaScript. JavaScript doesn't have operator overloading currently, among others. And together now, we basically have a spec that we have implemented in both Chromium as well as Firefox. And you will see demo of that. Now, the code for that would look like what is on the right side. That is essentially JavaScript code. We are not really changing JavaScript language. We are introducing one particular object that has these nice properties that can map efficiently to these vector instructions. So now let me show you some demos. So here I'm going to run a Mandelbrot demo. It's written by Peter Jensen. Now, when I run it, Mandelbrot is a classic example for vectorization that shows benefit of vectorization. The frame per second depends on the color that is computed. And when I start, you see basically 18, 19 frames per second, and it keeps going lower and lower. The darker areas need more computation. So eventually, it will go to 9 and so on. This is without SIMD. Now, if I enable SIMD, suddenly you go to about 3x, 4x faster speed up. So the question is, you want this, or you want this? And this is the latest browser, and all browsers. Now, if you come and profile this, again, thanks to the marvelous profilers and Chrome DevTools. Here I'm running it first on Chrome. And then I stop and then basically show you. You see here, about 70% of time is spent in this function. And this is the code that has been vectorized. You see, we have this SIMD object. That is all we have done. And it has all these nice properties, like when you say int32 times 4 splat 0, it replicates 0 into 4 elements. And then here, you have 2 JavaScript objects, you're multiplied by them. But again, remember, these are all 4 operations at a time. Parallel, compare, and so on. So if you look at the number of iterations here compared to the sequential one, you see that it is divided by 4. You get a speed up of 4. But this is now using SIMD. And if you are familiar, I don't know how many people, can you raise your hand if you're familiar with SIMD programming in the native world? OK, so some people are familiar. In the C code, if you look at this code, it looks very ugly. It's lots of if-defs, whether this is Intel, whether it's ARM, whether it's this particular operating system or the other. This is really elegant syntax. You just say SIMD, and it will work on all platforms. That is, the web runtime engine developers do the hard work to make it possible for you developers to write this code and be assured that it gives you significant performance. The major property here is guaranteed performance. That is, the JIT does not really reason about whether it can vectorize or not. It will do it for you. And then the JIT developers have to make sure that you would get that performance that you want. So now going back, note that this is lower level parallelism. If I ran the same demo, now, if you're familiar with web workers, this is higher level parallelism in JavaScript. If I run it, one web worker, again the same thing, it will eventually go to 9 frames per second. If I turn SIMD on, you are going to 3x, 4x, one web worker. If you add 2 web workers, you are getting like about 60, and so on. So this is a dual-core machine. And if I keep adding more, eventually it saturates. But that is like perfect. You basically have lower-level parallelism, higher-level parallelism. So this demo were done on Chromium. And you see all version of Chromium we have this working on. Now, I'm very pleased to tell you that it has also landed. The support for SIMD has landed in Firefox. And these demos are all available. The link is in the presentation. You can experience by yourself. Again, Firefox Nightly. Here you run very similar performance. If I turn SIMD on, you're getting to really good. If you keep adding web workers, you're actually getting higher and higher. So this is excellent. It already has landed in Odin Monkey part of Firefox Nightly. So, and then here are the performance on the benchmarks that we have developed. Everything is open. And you see with the float 32 times 4 and int 32 times 4, the theoretical speedup is 4, because you are operating 4 things at the same time. Nonetheless, in some cases, we are getting even better performance. There are reasons for that. I can talk about that. There's some nonlinearity things. There's some difference between float and double in terms of performance. But this is really good. This is like stable performance across the board. And different vertical bars are different processors. We have on Ivy Bridge, we have on Atom, and all of them you're getting really good speedups. So the current state is, it was presented by John McCutcheon and Peter with strong support from Mozilla at the TC39 committee, and it was unanimously approved to advance to the next stage of standardization. And I'm very pleased to let you know that Microsoft has also publicly joined this collaboration, so as well as ARM. So we have bi-weekly meetings, Intel, Google, Mozilla, Microsoft, and ARM. And to just make sure we design a spec that you guys can use and be confident that it's giving you significant performance. And we think this can be used to develop libraries, high-performance libraries for like games, image processing, signal processing, video processing, DSPs, etc. And this would make it possible. Once those libraries are there, average developer may not even need to know about that and just use it, but it will work great on essentially all the browsers that have the support for SIMD. Another adjacent technology here that we have been working is Emscripten that you probably have heard. Emscripten is a Mozilla technology, is a compiler from LLVM backend to JavaScript, replacing system calls with HTML5 calls. Now, if the original program, native program, had C++ intrinsics, then up until this work, Emscripten could not compile that because there is no way of expressing that vector parallelism in JavaScript. But with this, now we are completing that path so that if your original application, you have a game engine that has intrinsics in it, it will automatically be compiled to SIMD.JS. And this is really a big thing because over the past 2 decades, there has been tremendous investment in developing these high-performance, highly tuned libraries using these capabilities. Now, with Emscripten and SIMD.JS combined with improvement in JavaScript performance through type inference, the kind of thing that SIMDJS does, it's going to be really great. You can bring enormous amount of code, high performance, all in the web platform. So in addition to doing this, working with, before going to that, let me show you another demo. This, again, was developed by Peter. So it is, let me make it a little bit smaller. Okay, for some reason. This should have, let me just go back and come back. Yes, but the thing is missing here. All right, so here, basically the idea is to create as many birds as possible while maintaining frame per second above 30. And here we have, without SIMD, we are able to handle 117 birds. The computation that's needed is collision detection. And you see, with current runtime, we are able to handle 120 without SIMD. Now, once you add SIMD on, because now this implementation is using SIMD, you get to handle a lot more birds. And that is essentially, you are going to 300 and above. Again, because now you can process things more and more. And this is all, again, in JavaScript. So now we work with the major browser vendors to bring this technology to the web. In addition, and then we do that all in open fashion. And also we have a runtime called Crosswalk. And Crosswalk is essentially an open source project using Blink, Chromium, and WebKit, and put together by Intel. It releases very fast. Every 6 weeks, it gets the latest Blink and adds together, and then it releases with some enhancement for certain capabilities that Intel platform has. And it has a lot of advantages. I don't have time to go through all of them. But it is also a vehicle that we can bring you these technologies. So it is available in Crosswalk. And Crosswalk, you can embed it as a runtime in your HTML5 application. And another product that we have, Intel acquired AppMobi's tool business, and Intel XDK, cross-platform development kit, is an excellent IDE for designing, developing, testing, profiling, and targeting different app stores. And again, it by itself has a lot of major features and like, UI frameworks, Cordova APIs, etc. And recently we have extended that for IoT device also. And then SIMD support through Crosswalk is already available in XDK. You can develop an application using XDK that targets SIMD on Intel devices. So now I'm going to talk about moving to perceptual computing. User interaction is moving from traditional ways of keyboard, mouse, and even touch to more intuitive interactions based on sound processing, image processing, object detection, face detection, facial recognition, gesture recognition, and so on. So it enables a lot of essentially use models that are not possible today. And I mean, the area is broad, like scene understanding, etc. And this is considered a big thing that is coming next. And fundamental to that is 3D cameras, depth cameras, that I'm going to demo you some certain things that you can do with depth camera that is very hard to do otherwise. So as you know, with HTML5, we have WebRTC. You are familiar with that. Very basic. I just show you. Everybody, I mean, knows about WebRTC, right? Let me just give some just simple ones. These are from Google Code. You come here, you start. You basically see me here. I can get a snapshot. I can apply filter, another snapshot, etc. You can actually make peer connection, peer-to-peer connections, like Skype. You can have data channels, etc. And because the video and audio are programmable, now you can do really interesting stuff. So this is one of my favorites, the Magic Xylophone by Soundstep. So the idea here is that I can play a xylophone by just touching this. So what is happening, let me disable that. That is exactly the problem I want to talk about. You don't play xylophone by your head. But what it is, it's because it is doing motion detection. Here you see as I move around, it compares consecutive frames and then it finds motion. That is a very cheap computation. If it wants to do what is called edge detection, that is compute intensive. And it's not doing that, therefore it doesn't recognize finger or anything. So because I'm moving, it is playing that. Nonetheless, it's really a nice demo. On the other hand, now let me put on a 3D camera. Okay, so here I'm going to show you a native experience of like perceptual computing, but not based on web technology. That is, the computation part is not based on web technology. So here is Fruit Ninja, developed by an extension of essentially that by my friend Ninjin Hu. So the objective here is to cut these fruits without touching a bomb that will be dropped. And as you see, if I come here, I'm not cutting the fruit, but it will recognize my hand. So if I can, so if you are, well, game over, I didn't hit the bomb. But so you really want this. So now what is happening? This 3D camera, in addition to color per pixel, it also picks the depth, the distance of the point. Now, of course, it allows you to do a much higher resolution All right. But it also enables efficient computation because you can filter out things that are far and focus on the things that are close to you. Because not only you have the color, you have the depth. And then that would enable you to do really more compute intensive, including recognition and so on. So now I show you those demos. All right, so the same game, Fruit Ninja. Now this time is completely in the web platform. Ask for the camera, I allow that. So you see I'm here, and it doesn't cut the fruit. But it recognizes my finger, and it's very, very fluid. So very nice. That is just because now it has depth information, and it can really process, recognize my finger, and do all these operations. Now, going back here, let me show you the WebGL, this part. So you see, this is me, real-time, rendered, all in JavaScript, in the browser. Now you can actually come here and add RGB. Again, it asks for allowing that. And now you see me, both color and depth. Now you can really think about creating models and doing things that are really exciting. Again, real-time processing of this. Now, if you go back on the calls, you see if I start a WebRTC call, the first one you will see is just a regular video. This one is the depth stream, that is the point cloud. This essentially has all the depth information about every pixel. And this has combined together. Now, if you're familiar with the research in visual computing, perceptual computing, depth camera is a major thing. It is going to make things possible that are not possible without it. And it is coming. Now, what I showed you here was the depth camera. I show you creative camera. Let me show it to you. All right. Because I'm not sure you guys can see it in the back, this is 3D camera. This particular one has two cameras. One is RGB, one is infrared. And right now, it's like you have to install it. But the good news, it is integrated. So Intel RealSense integrates this into devices. So soon, it will be mainstream. This is one of the devices that comes with integrated depth camera. If you haven't seen Dell Venue, you basically, it has that. And it actually has really nice, and the camera is here. It has 3 cameras in the back, and all integrated. So, and there is a cool app that actually, you can take a picture, and then you can click and like measure the distance, and it basically tell you how much it is, and if you can see that. So, and then any 2 points, or and so on. So essentially, depth camera is being integrated. RealSense from Intel provides that, and it's going to be mainstream, expected to be mainstream on PCs, tablets, and so on. And then, so one of the works we have been doing is extending WebRTC with depth camera. All right. So I showed you this demo. You basically get the idea here. Currently, it is a separate device that you have to buy, but it is going to be, this is going to be integrated, or it's just coming. And then you can do amazing experiences with it. And then again, scene understanding, that's a major area that and then you can think about essentially both the client and cloud being involved in doing all this computation. So what we have done is essentially added this additional argument into essentially the get user media that is depth stream. And you will basically get this information, and they are synchronized. So the color and the depth are synchronized from the same point at the same time. And again, JavaScript, no plugin, no native code, just HTML5 API. And the good news, this is actually in the HTML5 proposal, that November 29 will be the proposal deadline. It's already there. So a lot of exciting things are, I think, ahead of us. Now, another gap is with web platform and native is basically wireless display. Now, it may be that for several reasons, you have a device and you want to project the display on larger display on your screen to larger display. Like you have a presentation on your tablet and you come here and you want to show that, and I want to see my own notes, but I want you to be able to see the presentation on large screen. Or you may have, it's supposed to have sound, like a movie I want to share. Or there's a game I want to control with my tablet. Now, all these, there are set of different wireless display technologies, fundamentally different from each other, like Intel WiDi, Chromecast, Miracast, Play 2, and so on. So we at Intel have worked out an API, HTML5 API, that it hides all these different implementation to the developer, and the application itself decides it wants to basically project that, and you use it in a unified fashion. This is, I think, another great thing coming from Intel. So I mentioned about XDK, Intel Cross-Platform Development Kit. It is a framework for developing, testing, profiling application. It allows you remote profiling on devices, even on older version of Android that is not possible currently. With XDK, you can do that. Now, we have extended that to IoT. And as you know, it is expected that tremendously large number of devices will be connected to the web. And essentially, they are becoming like extension of the web. They're like web servers that provide some data. And it seems JavaScript is a natural fit there. And you want to, and then Node already runs on a large number of them. So we have extended XDK to enable IoT programming. You can, of course, use XDK for the companion app. Typically, you have a program on the IoT device, and then you have a program on your, say, phone or tablet that controls that. And you can use XDK for both, end to end. For here, you basically can develop JavaScript programs, Node programs, that ship it to the IoT device, debug it remotely, all on your tablet under XDK, end-to-end programming of IoT device. So here, I will show you a demo of using Intel XDK to create an IoT device and to program both the companion application as well as the IoT device. So here, this demo was done by my colleague Dan Yocum from Intel, and he creates basically an RGB lamp using an RGB LED, a ping pong ball, and a bunch of other material. Now here it is here, and Galileo chip from Intel. Now and then using this, you can basically touch and control the color of your lamp. That is, on your phone, you touch, and then it will control the IoT device, which has this capability, and you see that. So now I'm going to play a video for you, which basically shows how this is done. And I'm going to speak to that. This is supposed to have, all right, here. So these are the material, the ping pong ball, RGB, PVC pipe, wood. And you see that thing. So the first thing, if it can be a little bit, all right, is to program the IoT device. So it is done using JavaScript. And then it actually wirelessly senses the IoT device. And it has a smarts for Node package manager. It will only select the parts that are needed, and it will push that to your IoT device. And then you can run it on your IoT device, but under the control of XDK. And say you find a bug and you want to go and debug it. So now it's running the remote debugger. The app is running on an IoT device, but you're actually debugging it on your, say, laptop in XDK. You can put breakpoints, you can look at variables, and so on. And once you are done, now you develop the companion app or the control app, again using XDK. XDK is free. Download that. No charge, including building the apps for all platforms. And then once it is developed, you basically see it just works fine. You see, as this is on the emulator is changed, the lamp color changes. But note that all development was done on XDK for both the IoT device as well as the companion app. And then you can basically, here, I mean, on the color palette, it just shows all the possible things. And then here are the acknowledgements for the music. So to summarize, HTML5 is closing the gap with native model. SIMD in JavaScript is going to enable a large class of applications. So browser is about to get a lot faster for certain domain applications like gaming, image processing, video processing, and so on. Great progress is being made there. Depth camera is going to make a new set of user experiences, very, very exciting. And it is already a part of the HTML5 proposal. And you saw also JavaScript is proliferating to other devices like IoT devices, and the programming of that is as easy as on just regular devices, thanks to XDK. So if there's one takeaway I want to take from here is that application model of the future is web application model. It's like HTML5 is the future application model. So call to action. download Firefox Nightly and experience SIMD. All the demos are available here, and there are more there than I just showed here at the bottom. And there are also links to our build of Chromium. So the status is basically, major part of it has already landed in Firefox. We have submitted the patch to Chrome, and our expectation is that it's going to come to Chrome this coming year, and great participation from other major players like Apple, as well as ARM. And XDK, free to download, and you can do a lot of exciting HTML5 development, application development. Now it expands to IoT, and SIMD again is one of the small features in XDK. And then Intel Developer Zone is here. It has a lot of resources and helpful information. So I have time for, I think, for 5 minutes for questions if anybody has. Go ahead.
Sure, so that Chromium build that you have there is a local build internal to Intel right now, is that correct?
Right, but it is available through the link that is in the presentation. We have made it available so you guys can just play with that. And I think it's probably 37, 38 version of Chromium is there.
The polyfill is available.
The polyfill is open available. That works anywhere. And Firefox, the Odin monkey part has landed. The Ion monkey part, Yvonne, my colleague, is there, is working very actively with great people in Mozilla to land it there completely so that it's there. I think combination of SIMD and in particular mscripting is going to be really a killer thing. It's like suddenly you can bring all these major applications that are going to become much faster in the web platform. And again, as I mentioned, now basically you have that all is needed to develop these libraries that are high performance, and you can basically hide the complexity of developing SIMD also through that. But the major missing part was there was no way in JavaScript to do that, and now there is a way. And we have bi-weekly meetings that, again, from all these participants attend, Google, Mozilla, Intel, and now recently Microsoft, as well as ARM. We welcome application developers. I mean, you come and tell us, or in other ways, what you need, the domain that you program. I mean, we would make sure that your input is taken to making sure that the spec is designed in such a way that your requirements are met, and also our implementations, you're welcome to give it to you. We give it to you open to play and then give us feedback. If it's not good enough, then we know that we have to improve them. Other questions?
Are these slides available? Your presentation slides available?
I expect that the conference would make them available. If not, just send me an email. I'll be happy. All right. If no more questions, thank you very much. Have a nice day.